In this session, we're going to talk about surface plates, and we're also going to talk about angle measurement, including sine bars, angle blocks, protractors, and more. Let's get started.
Hello, I'm Jim Salisbury with mp4 America Corporation, and welcome to the Metrology Training Lab. In this episode, we want to recognize and appreciate a piece of measuring equipment that rarely gets much glory, but is the foundation for much of the work done in this business, the granite surface plate. The surface plate is simply a big flat rock, designed stiff and massive to not distort, nice and hard to limit wear, and flat so we can use it as the reference in measurements. A typical measurement on a surface plate involves something like this height gauge, where either the part or the gauge moves around on the plate. An example calibration done on a surface plate is the calibration of micrometer standards, shown here, where the standard stands upright on the plate, and we do a comparison method using a gauge block and leverhead electronic detector like this mp4 mu checker. There is an American national standard on granite surface plates called ASME B89.3.7, which replaced an old federal specification called GGG P463C, which was used for decades. Both standards define the same accuracy grades for surface plates. The highest accuracy is grade AA, which is often found in laboratories, grade A, which is common in inspection areas, and grade B, which is more a shop floor grade. We have developed a nice technical bulletin on surface plates that includes some information on tolerances and calibration, so you can find that in our on-demand educational resources section of our website. There are two important flatness specifications for surface plates, and the tolerances are defined by the grade and the size of the plate. This plate here is 30 by 48 inches length and width, and it's grade AA. So based on the size and the grade, the overall flatness tolerance for this plate, in accordance to the standard, is 180 millionths of an inch. That tolerance applies across the entire surface of the plate and is a maximum separation form tolerance. From the highest peak to the lowest valley, the entire surface must lie between those limits and must be less than that flatness tolerance. Surface plates also have a smaller localized flatness tolerance, which applies over a much smaller area, about the footprints of a height gauge. That location variation in flatness is usually called the repeat reading in practice, which is an old historic term coming from calibration practice. For this plate, with the overall flatness of 180 millionths, the tolerance for the repeat reading is 45 millionths. Now, it's critical to get a surface plate calibrated for both the overall flatness and the repeat reading over time. We see in practice that some commercial labs will suggest skipping the check of the overall flatness. So be careful with this. Your surface plate calibration program needs to address both the local and overall flatness of the plate. With regular calibration and occasional relapping, your surface plate should last for decades. Your primary maintenance is mostly to clean it regularly. With such a large horizontal surface, surface plates can collect dust and dirt quite easily. There are a number of different cleaners on the market just for surface plates, but it's a rock. There are lots of options for cleaning. In our calibration lab, we have a clean room, so our plates don't get too dirty. But prior to any precision work, we will clean the area with denatured alcohol, which is the cleaner of choice in our lab. Our experience has also shown that a light stoning of the plates will improve repeatability. We like the larger Cerastone that we sell here at mp4. It works well for this job. Now, we're not trying to change the flatness, just a few passes with the stone to remove any little micro-inch contaminants. We like our gauges to almost float across the plate, like the puck in air hockey. In this episode, we just wanted to give you an introduction to surface plates and some things to consider in the calibration and maintenance of your plates. Thank you. I'm Jim Salisbury, and I'll see you next time from the Metrology Training Lab.
Well, welcome to the premiere episode of Gauging Quality. I'm Dirk Ducharme, Editor-in-Chief of Quality Digest.
And I'm Craig Howell, the owner of CPM Labs in Rancho Cordova, California.
Craig here has more than 20 years of experience in gauge use and calibration, which means that he brings that 20 years of experience to you guys to let you know how you use gauges, how you calibrate them, kind of the care and feeding of gauges, everything that you need to know about gauge use and calibration you're going to be seeing on this series of shows. But today, we're going to start with the basics. Today, Craig is going to show us how a surface plate is calibrated from start to finish. Now, if you have any questions during the show, remember, we're live, so send your questions to techno-live@qualitydigest.com. You'll see them there at the bottom of your screen, and we will try to get your questions on the show. It can be questions related to surface plates, what you're seeing today, or it could be some general gauging qualities. We'll try to get to as many of the questions as we can today. So, Craig? Surface plates, this is what we're talking about today. So why is this a good place to start with surface plates?
The surface plate is going to be the foundation of all your measurements. Your tools are going to be on it, the part you're measuring is going to be on it. The accuracy of your measurements will only be as good as your foundation.
Okay. Now, I understand, just so our users know, some of what you're going to see today was pre-recorded yesterday because it takes, how long did it take you to calibrate this plate?
It took about an hour to get this plate done.
Okay. So obviously we couldn't show you a complete calibration, so what we're going to show you is some steps. We'll talk you through it. This was some of the setup things that we needed to do, and then we'll show you kind of a demo of what a flatness measurement is, and also, what's the other measurement?
Repeat reading.
A repeat reading. And what's the difference between flatness? We're going to look at both those things today. What's the difference between flatness and a repeat reading?
Flatness is done on the overall plate. It's imagine two planes, a high and a low, and everything in between. It's a one surface measurement.
And a repeat reading?
Repeat is more of a localized, a 4 or 5 inch section. In this case, a 5 inch section within. So it's a tighter tolerance because you can't have as much variance in 5 inches as you can in 3 feet.
And you have to, this is what's required for an
the
official
federal
calibration.
spec, you have to do them. You have to do both. You have to do both. The flatness we'll do with our tools, and the repeat reading we'll also do. You cannot do just one and call it a complete calibration.
Okay. So step us through what you had to do yesterday just to even get to the point where we calibrate the plate.
All right. The very first thing we will do is look at the plate and see how level it is. It should be level, and it should be on 3 points. You'll see we're using a master level to see which end's high. They're never perfectly level when we start. So we do it in the other axis also, and we've determined that side is high. So you can see the bubble is pegged all the way to the edge. Now we're going to lift the plate and shim underneath it.
Now you're just using, that looks like a car jack?
It's a car jack. The plate is a little heavy to try to lift and slide a shim under. So we're going to shim it. Now you'll see the bubble is right in the middle. We're level. We're ready to start.
So all you did is you just jacked it up, and I noticed in your bag of tricks you had a bunch of aluminum shims from, looked like maybe a business card thickness up to, what was it?
Maybe a quarter of an inch, eighth of an inch.
So all you're doing is you're just basically just trying to get the plate more or less level as possible. And why is that? Why is the level important?
Ideally, you'd want your plate to be level if you can, if it has adjustments. A lot of times the 3-point setup will have adjusting bolts, or the feet will. In this case, we're on rollers. So the reason we had to be level is our machinery is so accurate, it can only take a certain amount of unlevelness to start. So we have to level it for the actual calibration of it.
Okay, and we'll get to the equipment that you use for. And by the way, how many surface plates do you do during the course of a year?
We'll probably do 3 to 4 a week, roughly.
So you do 150 surface plate calibrations a year or so?
Quite a few.
Okay. So you've leveled it. What's next?
After we level it, the next step we would do is we would clean it. We use a combination of a surface plate cleaner to get off all the dirt and grit, and we'll wipe that around, and it eventually dries and cleans off.
And this is just to get off any just general dirt and grime that's on it. Okay.
And then we'll look for smeared metal, which is real common, and that's removing smeared metal that wouldn't come off with the plate cleaner. aluminum, brass, copper tends to smear on there.
So this is where they've put equipment on there and they've moved it and it's left a residue of the metal behind, right?
That's right. And then we have to clean off our grit because anything will show up. So you can see we had to go back and re-clean
And what is it
areas.
you're using there?
That's called Cratex. It's an abrasive on a rubber compound. It's pretty mild. It'll just remove the material without hurting the granite.
And then again, you had to go back and clean off any junk that you put on as a result of even doing that.
Each time we have to clean. We have to have a clean plate to start. We cannot measure on dirt.
Because the dirt itself will affect the measurement?
It will. The entire tolerance is so close on these things as far as how they're specified. We have to be clean to start.
Okay. So level, clean, what's
After
next?
level clean, we would lay out for setting we're going to put a straight edge and move our levels, so we will lay out the plate as far as where we're going to position our straight edges.
So tell us what's actually, so here you're marking it up, but what is it you're laying out? Some sort of grid?
It's like a grid where we're going to lay our straight edge and we're going to put the 2 gauge heads along a straight edge. One of them will stay still, one will move. Right now I'm just laying out the center lines of the plate as well as the edges.
And this is just so you can line up your straight edge later on.
Right.
Okay.
Now I'm getting the straight edge in position. And then next we will be putting the gauge heads right beside them.
Right beside those. Okay. So show us where on a surface plate this grid is.
All
maybe
right.
if we can use the overhead camera, maybe we can kind of see what we're talking about
Sure. I'll
here.
start off with what we're going to do for our reference. Could you remove the amplifier?
Oh, sure. Yeah. Well, actually, let's leave this here for a little bit. I want to refer to this in just a
Oh,
second.
all right.
But you said that you're actually drawing. You're going to do three lines, and just show us where this grid is actually going
All
on
right,
the plate.
I will. It's an eight line grid is what's specified. And one of the lines goes this direction, then the second one, and then the third. Then we will do 3 vertical, or 3 on the other direction. We'll do 3 different runs.
Okay.
Then we'll do 2 diagonals. And that will give us our 8 lines that are specified that we should check.
Now, if you had a bigger surface plate, like an 8-foot by 10-foot surface plate, would you do more lines?
We would still do the 8. We would vary our spacing in between each measurement. For a small plate, we do a very, very tight spacing. We'd only move the gauge head a little bit for each one. For a large plate, we might go 6 inches instead of 4.
Okay, so
We've chosen 4 for this.
So no matter what, it's always 8. It's always 8 runs.
It's always
that
8
you're-
lines for the flatness check.
Okay, so we're going to get ready to do flatness right now, but tell us a little bit about the equipment that you use.
Sure, this is the Mar Federal differential leveling system, and it consists of 2 level heads, which are basically a pendulum, and they will move as the angle changes. That'll feed the amplifier, which has a current running through them, and we'll get a number shown in arc seconds.
Okay.
Then that will go over to the computer, and the software will calculate the arc seconds, and you'll get into that.
Yeah, well, we'll get into the kind of what's actually going on here as you're doing part of your demo. But one thing I wanted to point out is this is, I read up on this a little bit. The specs on this is 0.1, it can measure 0.1, or is accurate to 0.1 arc seconds. Like, well, what is 0.1 arc seconds? So I Googled it. 0.1 arc seconds is 28 millionths of a degree. I mean, that's
a
hardly
fine measurement.
hardly you breathe on it and it moves. So that's what it's capable of resolving in terms of any kind of shift in level is 28 millionths of a degree. That's pretty something else.
Now,
there.
the reason these are differential is there are 2 gauge heads and they're connected together. When we level the plate, we get it as level as we can, but there's always going to be a certain amount of unlevelness. This will compensate for that. If both heads happen to be slightly one direction, by zeroing them in a differential setup, that'll cancel itself out.
Oh, so if you've got a slight tilt
Slight
to the plate,
incline.
one measures minus, one measures plus, they cancel each
Comes
other
out
out,
to
so
0.
Okay, gotcha. So the only thing they're going to record is the difference between
Between them,
them. Okay,
the difference.
I'll get this out of your way.
Well,
Oh, and this is
while I'm
the
here-
controller. Okay.
While I'm here, I'm going to go ahead and set up my levels. This is part of what we would do when we're doing your plate. Is I've got to get them both to 0. That's for gauge head A.
So you're just zeroing out the levels right now.
Right. And let's get to gauge head B. And then we'll do both together.
So now they're zeroed out. Now, before we get, also tell us a little bit about what happens on the software over here. Maybe we can share the software screen.
All right. Let me point out what that's showing. What we have is our Moody plot, which is the 8-line measurement that you'll see in the upper right. You'll see the 3 one direction, 3 the other direction, and the verticals. It will be drawing a line as we do our measurement. I'm going to take our first measurement, so it'll start the grid. It starts at 0.
Now, I will say also this has already been pre-programmed with what, the size of the plate and how big each of your steps is going to be, is that right?
Yes, I told you the length of the plate and the spacing of my measurements, which is 4 inches. It does the math. On
Okay.
the 36-inch plate, and we start at 4 inches, and we're going to end at 4 inches in. It says 7 different data points.
Okay,
this direction.
you can just kind of program in the parameters, and it knows what measurements you're going to take and
tells me.
steps you through it. Okay.
So I've done my first one. If we go back to the live, there we go. I'm going to go ahead and take my second measurement. I'll be doing, it looks like 7 of these.
So one level stays in place, and you move the other level 4 inches.
Yes.
Okay.
The B level in this case stays in place. That would be our reference level. That one was, they've both been zeroed, and that stays still. So I'll just take a number of hits here. Each time I do, the machine records the data point. I move 4 inches. I have to let everything settle down. Take my data point, and it draws the line as we go. Just about through here. Looks like I've got a couple more left.
Okay, so I see in the upper left here, that's actually showing you the difference in level, which is also the difference in height as you're moving along.
Right.
Okay.
And the numbers will be both plus and minus depending on how the plate is worn, which direction the level's tilting. This is the final one for this one, and now it shows that path.
Okay, so it shows off, we start off with a little bit of a dip, and then we come back up, and then a little bit of a peak. So we actually are showing a little bit of a dip in that part of the table then.
That's correct. So that's what one path would look like.
Okay. Why don't you do another path, and I'll explain really quick kind of what the math, what the software is kind of doing. Just anybody's interested to actually how you're getting a difference in height just from a level. Some really simple trig, and I'll show people what's going on with that.
All right, I'll do another run.
That's assuming I can find my pen, which hopefully is right in my pocket. There we go. Good. All right, if we come up here to a little blackboard here, get some ink in my pen. So what Craig's showing you, so we have our little reference level, I mean the one that stays in place, and that's down here. And we're going to extend the baseline of this. Okay, so on his first measurement, let's say, we'll just really exaggerate, this goes uphill a little bit, and there is our second level. That's the one that we're doing our measurement with. What we're trying to find is that height. Why? What do we know? Well, some basic trig here. You know, if you have the length of any line and an angle, you can figure out anything else on a triangle. So, we have this angle. We know that angle because it's been given to us by the level. And we know the length of this line because Craig's already told us. He's doing 4-inch steps. So we've got an angle, we've got one length, now we can calculate y. If any of you remember your trigonometry, sine of the angle is equal to the opposite, which is y, over the hypotenuse, which is 4 inches. Multiply both sides by 4. 4 inches times the sine of that angle. Let's say that angle, just for giggles, let's say that angle was 1 arcsecond. I know that 1 arcsecond is equal to 0.00028 degrees. So 4 times sine of 0.00028 degrees, that is going to give me my height. That just happens to be, if you want to do the math, you can check me on this, about 20 micro inches. So over 4 inches with a 1 arcsecond change in level, that is going, y is going to be, this height is going to be 20 micro inches, meaning that this point is 20 micro inches higher than that point right there. And obviously, he keeps stepping across and doing that calculation over and over again. Or I should say the software is doing that calculation over and over again. So that's basically the math behind it. That's all that's going on. Now, you did another run here. So obviously, yesterday we did all of these and calibrated, and I believe we got results from this. Maybe we can bring up the results of what our flatness run was yesterday.
All right, there it is.
So this is actually this plate.
And there's the 8 different lines, And where it says reference and letter A, that was our first path. That was the one we just showed you now. It took the same shape, dipped down, went up a little bit above. Then you will see on the right side, it does say maximum elevation, I believe that's 147, 148 millionths.
Okay.
On this plate, a 2 by 3 foot, there's different grades, grade AA, grade A, and grade B. This was originally made to a grade A, and it meets the spec. The grade A spec was 200 millionths for flatness.
And we measured?
We measured 148.
148. So we are within the flatness spec for a grade A plate. Now, actually, if we can go back to that results screen again, I'm going to ask you a question. You've done a lot of surface plates. You probably recognize different kind of plots. I happen to know how this thing was installed in the shop. I want to I'm going to test you and see. You tell me how it was installed in the shop.
Well,
I noticed this really. Okay, well, yeah, I won't say anything. You just tell me.
I see right by the word reference, it dips down, and also to the left, about the middle on the left, it dips down. So I would suggest somebody was standing or working where it says reference, and they wore the plate in one area, which is habitual. People do that. Always work in the same place.
There you go. I'll tell you exactly where this was mounted. I got this from a machine shop up near me, up in Colfax, California. This was sitting on a bench against a wall. And so this was the front, and the workman worked on that side of the table. These sides weren't accessible, and neither was the back, obviously, because it was on a bench pushed against the wall. So that was his workspace right there.
So they do recommend rotating the plate every year or so, and that way you can even out
so you don't keep
the
wearing
wear.
out one spot.
You're right. So you don't make the dip any larger.
Okay, but even though that was worn there, it's still within spec.
It's well within spec on the flatness. It meets the grade.
Okay, I believe we have a question coming in.
Oh.
If we can get that up on the screen, I'll take a look at it. This is a question from a viewer. By the way, just as a reminder, if you have any questions about what we're doing or anything else related to gauging, send your questions to techno-live@qualitydigest.com. This question is from Joe S. We're moving to a new facility and need to move our surface plate. He doesn't say how big it is, but what things should we consider?
Okay, the two most important things from the surface plate point of view will be the temperature change. You're going to go from a lab environment, usually 68 degrees, into a moving truck possibly, in summer possibly, in winter. It's going to change quite a bit. When it gets to where it's going to need time for the temperature to normalize throughout this granite. It's rock. It does change in dimension as it gets cold or hot.
Okay.
So it's going to need to temperature stabilize. The other is the weight involved. Large plates can weigh tons, and basically they're touching the ground at 4 points a lot of the time.
On their base?
On their base, 4 bolts or 4 wheels, so that the floor will tend to dip down a bit if it's tons.
Okay.
So I would suggest first let it sit in the temperature it's going to be living in for at least 2 or 3 days. Depends how much variance you've seen. We had a company that moved in summer, and it went from a 68-degree lab into a 110, 120-degree truck, and then into a very humid environment to move it into the building. It took a while for the plate to normalize.
So you're saying you need to let it settle literally physically into place, and temperature-wise needs to soak, just like you would soak anything in your
just
your
any
calibration
precision
level, right?
gauging. Yeah, it needs to sit in the right environment.
Okay, so we've done a flatness measurement. What's the next?
The next step would be the repeat reading, and we have a separate gauge that checks that.
Okay.
I'll go ahead and get that ready.
I'll move these out of the way for you.
Now this gauge, we're showing a close-up so you can see the indicator. What it is an indicator on a fixture, and it's going to measure that local variance over a 5-inch span.
Actually, if we can get the wide shot here again, Daniel, I just want to show the whole thing here. Okay, so this is this is called a RON...
Repeatometer.
Repeatometer.
Yes.
Should echo a little bit after that. From the 40s or 50s, I'm guessing.
The design is.
And then you just got a regular dial indicator.
It's an indicator and a 5-inch section.
Okay.
And then there's the base. What it simulates is a gauge block and a height gauge. If you were to move that around the plate, how much variance just due to localized wear would you see?
Okay.
That's the repeat reading.
And let's go back to our close-up here.
All right. Get that set up, and I've tried to zero. What we'll do is move it all throughout the plate, and we'll look for the variance, and it's a much tighter specification than the flatness. I'm going to move it some, and we're going to see how it moves. You can see the indicator is It moved almost a tenth there. I'm having trouble keeping it on screen, but that's just me.
Now, each of the small ticks is how
20
much?
millionths. So we saw about 80 there.
Okay.
We saw about 80 millionths there.
Okay, so just over that little 10-inch area you move this, we saw 80 millionths.
Right, that was an area of wear. You know, the inspector that worked at that area was doing his job. He was working.
Now you got to do this over the entire plate.
You're right. We'll follow the similar path that we did with our flatness machine.
And as you're moving it, you're just looking at the gauge and just looking at the deflection on the gauge there.
You're right. I'm looking at the highest high and the lowest low, keeping track. On this circumcised plate for a grade A, it's allowed 70 millionths on repeat reading and 120 millionths on grade B, which is the lower grade.
Okay, as you're continuing to move that, we have a question coming in.
Oh, good.
What other methods are employed to calibrate surface plates? That's a good question. So before we had something like an AMAR, the MAR Federal Differential Leveling System, which is what you use, what did they do?
Previously, I had a planicator, which was basically they call it a straight edge in the spec. I call it a vertical surface plate. It's a very flat piece of granite suspended on 2 points with, again, it had a MAR indicator on a stick that we would slide under one end and zero it. Very time consuming, very accurate, but you could only do as large as your planicator was. They make them in 2 foot, 3 foot, and 4 foot. We do some pretty large plates, and at times a 4 foot section, you'd be there all day.
Well, I was just going to say, so aside from the cleaning part, do the flatness measurement on this plate took you how long? Just the actual?
It took about 40 minutes. I'd say 35 to 40 minutes for the actual flatness.
And with a planicator?
At least an hour to do a good job, to do it accurate.
Okay. Interesting.
So that, as far as the repeat alternatives, it doesn't matter what brand, several people make them, but they do call out both the flatness and repeatability.
And what was our repeatability?
Total repeatability I saw was 120 million. So although the flatness met the grade A, the repeat was worn to the point of grade B.
Yeah, so what was, for a grade A, what should the repeat have been?
70.
Okay, and
70
we were
max.
at?
We saw 80 within our little span.
Okay, and I think you said 120 over the
120
whole.
was total, which
So
it meets the grade
basically,
B.
this is marked as a grade A plate, but, so I guess no, we bought this used, obviously. So I guess if you're buying a used plate, which you can get them pretty cheap, this was $200, plate and the stand, but unless it has an up-to-date calibration sticker on it, you don't necessarily know what you're getting.
No, you'll need to have it checked. That's what we do. The good news is they do resurface them. The surface plate companies, we deal with several. Our favorite is Standridge Granite. They resurface them to any grade you need.
Okay. Now we have another question coming in.
Okay.
Our plate, no, I don't think we talked much about this. Our plate does not have the 3-point support. What should we do?
The 3-point is the most critical. As I mentioned, when they quarry the rock, they glue the 3 pads on, and all processing is done from that point on 3 points. If it doesn't have the 3-point system, and answer your question, put them on. It's common sense where you put them. You do a tic-tac-toe style grid. You'll put 2 on at 2 intersections and 1 a third of the way down at the other. You'll have 3 different points. It's so the granite it doesn't really sag, but it'll normalize to the right levelness. That's one of the most important parts, is having that 3-point system.
Okay.
That's more important than level.
And I think we have another question here.
Okay.
And there we go. Okay, well, this is good. I mean, look, we have a desk lamp. The question is, we have a desk lamp near our surface plate to illuminate dark features. Is this a problem? And I've seen this too. Matter of fact, where I was at with where I bought this plate, it was kind of it was kind of a home machine shop, and he had a little gooseneck lamp right over the plate so we could see what he was doing.
The quick answer is yes, that will be a problem. The federal spec mentions if the top of a plate is 2.5 degrees hotter than the bottom of a plate. That's not a lot of difference. On a little 2 by 3 foot plate, it'll bow up enough to show it being out of tolerance with a grade A if the plate was perfect.
Okay.
Just due to the growth of the material.
Okay. Just a reminder, if you got any questions, get them to us, techno-live@qualitydigest.com. There you go. You see it at the bottom of your screen, techno-live@qualitydigest.com. We just have a few more minutes here, but get your questions into us.
All right.
Now, my question came up, and we were talking about this earlier, and I think you had a way to show us, is when we talk, this surface plate has to be accurate within 200 microinches. And the
Yes.
question was, how big is 200 microinches? When we say not any more variation than that, what do we really mean?
Let's do an example where we can show you, because a lot of times we'll be asked, what does 200 millionths mean? What does that look like?
Okay.
So
you need your
I'll need my levels.
back. Okay. This was actually kind of amazing to me. There's
Down
your-
on there.
there you go.
And can you activate my computer screen? What I'm going to do is get these two levels side by side. I'm going to zero them. All right. So now these are zeroed. Now,
Just happen to
a
have
piece of paper is almost 400 millionths. It's almost twice the entire tolerance we're allowed on this surface plate. This is almost twice the tolerance.
So,
Let's
the,
put
so the
that-
question, will the level detect it?
Will the level show it? So let's go ahead and lift it up and put it on there. And we'll see if this happens to show up on
If we go to our screen share there, we can
our
see the actual.
system. Well, it showed up. It
This is
shows-
showing 195 arc seconds.
Arc seconds, yes.
Which I know from doing the math is about 400 microinches, which you said is about the thickness of
About
a
this.
piece of paper. So this paper is actually twice as thick as what the allowable standard is for this surface plate.
You're right, and it would show up. So we can resolve much finer than that. If we were to have put this thing in the finer mode, we would actually see 10th.
Okay, and we actually have
Of
another
seconds.
question.
All right.
Have there been many upgrades or improvements to the measuring equipment that you are using? Have there been improvements over the years? That's a good. When did you get this?
I got that about 6 to 7 years ago. I'd always wanted one.
Okay.
Because these make the job so much more predictable, so much easier from our end. The customers love the graphs. They just, the whole setup works well. Yes, there have been improvements. We started out with the planicator, which limited us to however long the planicator itself was.
And with this, there's no limit really to the size of the plate.
They're 20 or 30 feet long cords, so we do some large plates.
Actually, I'm glad you brought that up. I think we have a picture of one of the plates that you did. One of the
Sometimes
large
we do
plates
some
that you
large
did.
ones, yes.
Yeah, this one is reasonably large size.
There we go.
So how big is that plate?
That plate was about 14 feet by 13 by 14 feet.
Okay.
I had to walk across it to
And
do
that was
my
a grade. I
diagonals.
think you told me that was a grade B plate,
The grade B plate.
which means the total flat variation of flatness is what across that?
Oh boy, it would be in the thousands on something that large. I don't recall the actual number, but
Okay.
it was well within. It took them 2 forklifts to move it into the facility. It was huge.
Well,
And when you have to walk across it, you know it's large.
okay. I think we have another question.
All right.
Am I right? Oh, there we go.
Okay.
Oh, okay. This is good. I've seen this where there are things, I don't know, I guess.
Ledges.
Ledges, okay, clamped to the edge. So does that affect anything?
The plates are made with that in mind. The ledged plates, that's what they're for, is for a clamp. You don't want to be overly aggressive. You don't want to use the C-clamp too hard, but they also, some have threaded inserts, just ways to hold the part down. Sometimes you have to, and yes, you can do that. You just have to be a little cautious.
Okay, we have another question.
All right.
Gauging quality. Okay, what specifications? We've been talking about specs. What
You're
are we
right,
talking
you're
about?
right. We're referring to the federal specification, which is, I believe it's GGG-463C. I'm not positive exactly, but that's close.
Those numbers sounded really good. Okay.
It is a federal specification that the plates are manufactured to, and in our case, we maintain them to that, and we certify them to that.
And I believe you said the best or the finest is AA?
AA is lab grade, that's the highest grade. Grade A is inspection grade, and grade B is also called shop room floor or tool room. It's the lowest of the federally accepted grades. Below that, it has to be resurfaced. It can't be certified.
Okay. And the specification obviously changes with the size,
With the length.
with the length of the plate.
Right,
Okay.
a 2-foot plate has a lot tighter spec than a 20-foot plate.
Okay. Were there any more questions there? Oh, we got another question. Great. Awesome. One second there. That looked like the same question.
We could answer it again.
We got time. Are you still getting it? Okay. Well, as he's getting the... Okay, we got it? There we go. What kind of adjustments can you make short of resurfacing the plate?
You really can't adjust the granite as such. It's ground down by the resurfacing process. If it's mounted incorrectly, then you can make a major adjustment, mounted on the 3 points. When we get them and they're on 4 point, right away we say either get a stand with the 3 point or make some cross members. The granite will move quite a bit.
Okay.
It'll go back to where it was originally processed.
But I believe you did say that you could also have them resurfaced or lapped, right?
They do relap, they do resurface. But this was other than that.
Is that worth doing?
Yes. The granite itself is already stabilized and normalized. It works really well. And when you get a quality outfit that will resurface and do their job right, the plate is better than new.
Do they do it in-house?
They do it at your facility.
Okay.
They travel around and do it. It's a heavy job.
So for instance, this plate obviously is grade A in flatness, but
Yes.
it is deteriorated. It's been worn, so it's grade B. So they could actually bring this grade B now plate up to a grade A.
Or double A, depending. They won't do double A if it's sitting on the floor just because of the environmental changes day and night and day and night. But yes, they can go to any grade you want.
Wow, and they just do it. Okay, great. Do we have any more questions, Christopher? Nope, that's it. Okay, well, great. Well, man, we covered a lot of material today, Craig.
I enjoyed it.
The Starrett C183 steel protractor is a fairly simple tool which is great for determining or setting angles to within a degree. With a 0 to 180 degree scale in each direction, you can read both angles and supplementary angles directly. The flat back and square head add to its versatility. You can use either side or the top against a reference surface to set or determine an angle. And probably most common, hold the bottom side of the head against an edge. The rust-resistant satin chrome head finish make the marked graduations and figures easy to read. The lock nut securely holds the 6-inch leg in any position. This aluminum block is being prepped for a machining center, but first we are going to lay out angles and cut off corners to shorten the cycle time. For each corner, use a rule and scribe a mark 1 7/8 inches from the end. Next, set the protractor at 45 degrees and lock. Then, using the rule mark as a guide, scribe a 45-degree cut line on each corner. Using these lines, you can safely cut off corners with a vertical bandsaw. After machining, each corner will have a 1-inch, 45-degree angle. Here's another app. You can determine the included angle of a cutting tool tip by holding the blade against the tool shank and positioning the head against the cutting edge. The C183 is not the tool for inspecting precise angle tolerances, but it is accurate to within a degree, which meets many requirements.
Today on This Old Tony, let's talk about angles stuff. Okay, fine, hold on a minute. The plan was to avoid using this word at all costs, but in this video, we're basically talking about trigonometry. Now wait, I know you hate that word. You've probably hated it since high school. I can't blame you. And that's why it was renamed shop math. Let's talk about sine bars, maybe sine tables, potentially angle blocks, why they work, and how you use them. We may get into cosine error, and if there's time, how to use all this math to take finer cuts on your lathe than you thought you could. All of this stuff, or all of the things I just mentioned, come down to trigonometry. I mean shop math. If you put my back to the wall, I'd tell you trigonometry is actually pretty cool. Totally worth giving it a second chance. Now, I realize trigonometry is a big word. It's got a lot of letters. Maybe that's why shop math works so well. But that said, there'll be very little math here. I'll leave that part up to you. Anyone that might be allergic to numbers, well, no hard feelings if you want to skip this video. Let's start at the beginning. Trigonometry comes from two words. Trigon, who was a famous Targaryen mathematician and inventor of the trigon insert, and ometry. I have no idea what that means, but there's probably a good Irish joke in there. Alright, enough screwing around. Settle down now. Do you know what this is? It's a sine bar. Come on, I literally said that not 2 sentences. And this magical, indispensable piece of shop equipment, if you do your part, can
set crazy precise angles. Machining isn't all square parts or round parts, you know. Sometimes there are angles. And I'm not talking about those out of square parts you usually make. I mean intentional angles. Precise intentional angles. Need to make or measure a surface to exactly, I don't know, 10.123 degrees? Well, this is your ticket. Use it on your surface plate, on your mill, surface grinder, lathe, backseat of your car, wherever and whenever you need to make or find an exact angle. I know what you're thinking. This old Tony, how does that chunk of metal do anything at all other than make me spend even more money I don't have? Well, I'll show you. If we put this down on a flat surface, imagine for a moment my bench is a flat surface, maybe like your surface plate. It doesn't do much of anything at all. It's a good paperweight at best. But once you put fresh batteries in it, if you stick something under one side, check out what happens. The top, magically, is not horizontal anymore. It's at an angle. You walked right into that. If instead you put something under one of the pins and the top isn't at an angle, if it looks like this, check your batteries. But of course, just whatever that random angle is, isn't very useful, is it? Heck, we could have cut an angle like that on the mill without the dumb sign bar. But here's the thing, with just a little bit of effort, and maybe a calculator, we can know what that angle is just by measuring how big or high that something is we stuck under one side. In this case, that's about 2 inches, or 50 millimeters, more or less, which can only mean one thing. The angle that this sign bar is now set to is exactly 23.578 degrees. All thanks to a little bit of trick shop math. The thing that really blows my mind is that those two things, the height and the angle, they're related. You can't change one without the other changing. How on earth does the sign bar know that the height changed? How does it convert it to an angle? And how does it do it so precisely? Well, I wouldn't be so bold as to claim to know the will of the gods, but what I can tell you is this, and don't panic, hopefully this should make more sense in a minute. The angle the sign bar makes with the table in this case is the inverse sine of the stack height divided by the length of the sign bar. In other words, the height of that stack is the length of the sign bar times the sine of that angle. I mean, technically those aren't other words, those are the same words, just said in a different order. And don't freak out, if sine or inverse sine, sometimes nicknamed arc sine, scare you, it shouldn't. Take a deep breath, let that high school trauma fade away, and you'll see they're right there on your calculator. It's a button just like any other button. Push it and the calculator will tell you the sign of whatever number you entered. Put in 30, push the sign button, and the calculator will tell you it's 0.5. And fun fact, the shift key on your calculator isn't just for typing capital numbers. Push the shift key, or the second function key in my case, and the sign button becomes the arc sine button, the inverse sine. Put in 0.5 and ask for the inverse sine, you get 30 degrees back out of it. If you'd rather not put your life in the hands of a calculator, you can also find these numbers in the back of the Machinery's Handbook, or probably any old high school math book. I guess I lied, it's not in the back, it's somewhere up near the front, but if you still trust me, have a look. The sine of 30 degrees is 0.5, just like the calculator said. Since we're here, and we're both just sitting around doing nothing waiting for the next really cool This Old Tony video, and to distinguish this a bit from other sine bar videos, let's have a very quick look at exactly what sine and cosine means, since I'll probably be dropping those words the rest of this video. That, and with any luck, will drive home the sine bar equations we just saw, so you're not just taking my word for it. You're not just trying to memorize something. Somewhere about 3,000 or 4,000 years ago, people were dying left and right from their ladders slipping away out from underneath them. Those were brutal times. To solve the killer ladder problem and ensure the survival of the human race, they invented trigonometry. Coincidentally, that's where the whole bad luck from walking under a ladder comes from. Check this out. This sine bar has 2 pins attached to it that are a very specific distance apart. The distance between those pins is exactly 5 inches. In theory anyway, depends on the quality of the sine bar you buy or you make. So does this sine table. The pins on this table are also 5 inches apart. We'll talk about why that's 5 a little bit later, but for now, these two things are exactly the same, except one of them is bigger. Can you guess which one is? But let's just look at the sine bar. Sine table is exactly the same thing. If we keep one pin still and only stack stuff under the other pin, the whole bar table moves in a circle. A circle with a radius equal to the distance between those pins, like a compass, right? When you're drawing a circle. And the higher we raise it, the larger the angle gets. Let's now take my fake flashlight and shine it at the sine bar, or sine table, or life-ending ladder, whatever. Note that I'm shining the light in from behind the angle of interest, in this case along the length of the bench it's sitting on. Because of that light, imagine for a moment our sine bar casts a perfect shadow. Now, this isn't a perfect example because our sign bar has some thickness to it, so imagine just the top surface, that line, is casting the shadow. That shadow it's casting, the length of that shadow, is related to the angle. The steeper I make the bar, the longer the shadow gets. Now, there's a relationship there, and the relationship between the angle of that line and the length of that shadow it makes was given a funny name. Sine. The length of that shadow is the sine of that angle. Now if I shine that flashlight down from the top, 90 degrees to what we were doing before, I get another shadow. This time next to the angle instead of opposite the angle. Since they were evidently running out of names back then, that shadow is called the cosine. So as we change the stack height, as that bar moves up and down through whatever angle, the length of both of those shadows changes. Now since our bar isn't changing length, hopefully it's apparent that the length of those two shadows are related. If the sine shadow gets longer, the cosine shadow has to get shorter, and vice versa. Now since there wasn't all that much to do 3,000 years ago, and most of their friends died slipping on ladders, they had plenty of time to give that relationship its own name too. In any given position of our sine bar or ladder, the length of the sine shadow divided by the length of the cosine shadow, they decided to call the tangent. And that's exactly what this is, a tangent. So let's get back to sines and cosines. Probably doesn't take too much imagination to see that there's a special point I can rotate this bar to, such that the length of the sine shadow is the same length as the cosine shadow. Can you guess what angle? Yes, 45 degrees. At 45 degrees, the sine and the cosine are exactly the same. Let's check the book. This lists sine, cosine, and tangent all in the same line for any given angle. You could see at 45 degrees, the sine and the cosine is the same. And now we know why the tangent is 1. Since sine and cosine are the same, those two numbers divided by each other is 1. This is fun. Let's keep going. So you don't sound like an idiot when you're explaining this to your friends down at the bar. The shadows we've been talking about are usually called the projections. This is the projection of the height, and this is the projection of the length. While we're here, there's one last thing I'd like to reinforce. Sine and cosine depend on which angle you're talking about. In our case, we were talking about the angle between the table and the top of the sine bar. If you wanted to talk about this angle up here, you'd have to switch your projections. That angle's shadow, or projection, would now be down here, and that would be the sine. And its cosine would be over here. That is sometimes tricky to keep track of, so be careful. If you decide to start projecting yourself onto your triangles, just make sure you're doing it right. For the three of you that are still watching, there's one last thing we should talk about so these numbers actually make sense in the real world. Back when Trigon was trying to help everyone out with their ladders, there was one big problem he couldn't quite crack. Everyone's ladders and sine bars were at different lengths. Trigon's calculators, slide rules, and tables didn't work for everyone. And tragically, even more people were dying now. Then it hit him. Yes, it was probably a ladder. He would assume everyone's ladder, sine bar, sine table, giant Christmas tree, lookout tower, cable car wire, whatever. He would assume they were all one long, just one unit. Doesn't matter what, 1 inch, 1 foot, 1 meter, 1 mile. If everybody agreed on one, the sine and the cosine could work. Let's see how that works for our 5-inch sine bar. Since our actual sine bar is 5 times longer than the one that Trigon got all hung up over. Now we have to multiply by 5. If we wanted to construct, say, a perfect 30-degree angle using a 5-inch sine bar, just like before, we need to figure out the stack height. So stack height is the sine of 30 degrees, which we saw is 0.5, times the length of the bar, times 5 inches. 0.5 times 5 is 2.5. Since we're working in inches, that's a 2.5 inch stack height. If our sine bar was 5 millimeters, that would be a 2.5 millimeter stack height. If it was 5 miles, that would be a 2.5 mile stack height. So now that we've packed 5 years of math classes in 5 minutes, let's talk about what you might stuff under your sine bar. Now, although for the stack you could technically use anything you wanted, usually, and especially when you don't want to get fired, you'd build the stack up with gauge blocks. This is a set of precision gauge blocks, or it used to be anyway. Now they're more like my fabrication blocks. But anyway, you pile these up like Legos to get to the dimension you need. For our 30-degree example on the 5-inch sine bar, we need to build up a 2.5-inch stack. So I'd grab the 2-inch block and the 1/2-inch block. The 1/2-inch block. Make sure your surface plate is meticulously clean. Get the blocks that you need, clean them, ring them together. Mine don't really ring anymore. And set up your sine bar. Now, of course, you don't need to use a 2-inch block and a 1/2-inch block. You could use 2 1-inch blocks and a 1/2-inch block, 5 1/2-inch blocks, 25 1/10-inch blocks. Machining knows no creative limits. As long, of course, your stack is the right height to get you the angle that you're hoping to work with. Now, you take the part that you want to inspect. something that has a 30-degree angle, like this 30-degree angle block. This is out of an angle block set. These are really handy to have, not that expensive. Not as expensive anyway as the gauge block set you'll need to go with your sign bar. But whatever you got, you put the part on the sign bar, and now we can come in with an indicator. This is a tenths indicator. Each division there is, I guess, 2.5 microns. I'm just going to zero it out, and then sweep the leg. Sweep the surface. Frankly, I expected that to be worse, given how I just threw everything out here on my surface plate. But that's reading 1/2 tenth of a thousandth of an inch, aka 1/2 tenth. That would be 1.25 microns. Now, of course, it depends on what you're measuring, but it often helps to build your sign bar fortress up against an angle plate of some kind. And usually, the back of your surface gauge will have pins that you can deploy. They'll stick out the bottom. Now, it's hard for me to show you, but you can use that to ride along the edge of your surface plate. And that way you can be sure everything is nice and straight. You're doing a nice clean sweep across the surface. You don't want your stuff falling over or introducing weird compound angles that could give you errors in your reading. Now, working with a sign bar to actually do machining is in principle the same exact thing. You'd set up your stack horizontally or vertically, however you need to get the work into the position to make your cut. That sometimes is easier said than done. Take this 5-inch sign bar, for example, on my mill. There's really no way to get it in the vise. It's just too big. This worked well when I had the Bridgeport, had a larger vise, but in this smaller vise, the sign bar is just too big. I could potentially use a parallel in the bottom of the vise, but it doesn't take very much to get out of the clamping range of these jaws. I could clamp onto the sign bar, and there's really not much room left for my work. If you imagine that on a parallel, with some angle to it, I just couldn't clamp the work. Ideally, I guess I'd be using a smaller sign bar here. Now, similar to what we saw on the surface plate, I'd probably set something like this up on an angle plate. I could clamp the angle plate down, then clamp the sign bar and the work to the angle plate. There is, of course, a limit to how big the work can be, so your setup would likely change a bit. Now, in practice, most of the time I can work with this little angle block set. Not as flexible as the sign bar, but I can mix and match these to get, the more popular angles, and they're much smaller, more compact. In this case, fit nicely in this vise. For bigger work, I've taken to using the sign table, though I bought that mostly to work on the surface grinder. Again, the function is exactly the same, and the only difference is this has sort of this subplate. One pin is hinged at the front, and there's a pin at the back you can build the gauge blocks under. Then just lock down all the screws and attach your work to the top. If and when you go shopping for sign bars, you'll find that one of the most popular sizes is 10-inch, twice the size of this one. I'm not totally sure why, but I'm willing to bet it's because 10 is an easy number to multiply by. Any answer you get on your calculator is a lot easier to multiply by 10 than, say, 9. This perhaps was in the land before calculators. But practically, the sign bar can be any size at all, though the longer it is, the more precise it usually is. And of course, you should match it to the size of your work. You wouldn't want to use a 1-inch sign bar to set up a 24-inch block of material on your mill. After 10, you'll find a lot of 5-inch bars like this one, and smaller 2.5-inch bars. Again, I think the idea used to be you multiplied by 10, because that was easy, then divided by 2 in the case of the 5-inch bar, or divided by 4 for the 2.5-inch bar. On top of that, I think most mechanical trades books, manuals, that sort of thing, already list sign tables based on bar length. It's been a while, but I think I've seen those. Before buying mine, I actually made one of my own. I don't remember exactly what I needed this for, but I made it wider than your usual sign bar. I did my best to set these pins 5 inches apart, but they're brazed in place and they moved a little bit. To figure out that center distance, I just put a reference angle on the top and built a stack until the indicator sweep over that read 0 from one side to the other. Very similar to that 30-degree angle block we saw a minute ago, except I have a small granite standard. When that indicator sweep read 0, I could just do the math backwards. I knew the angle, I could measure the stack height, and it turns out the distance between centers on this is 5.020. Then I just stamp that into the bottom and use that number anytime I use this sign bar. One last thing before we wrap up the sign bar topic. You'll often hear that sign bars are only good to about 45 degrees. That's not really true. If I were to venture a guess, that may be rooted in the fact that most sign tables in the back of old machining books only went to 45 degrees. Now they only went that far, I believe, to save on printing. Anything over 45 degrees, and people used to know how to do the math. If you needed to know the sine of 60, for example, and your chart only went to 45, well, you knew that the cosine of 30 was the same same value. So you'd find it that way. Though there is an upper practical limit to the sine bar, and that's about 60 degrees. In fact, on most sine bars, if you try to go above 60, you'll run into the actual body of the bar, down around here, below the pin. I haven't measured this, but that looks like it's pretty close to 60. The real reason goes back to the fact that the sine bar, as you lift it, traces out a circle. You remember this bit? Down in the lower range, up to about 15, maybe 20 degrees, sine bars can be crazy precise because the change is almost linear. Double the stack height and you almost double the angle. But as you wrap up around the circle, you're getting less bang for your stacking buck. As you approach 60 and beyond, the curve of the circle starts to flatten out a lot. Very small changes in stack height up there can result in big angle changes. My lathe is smarter than me. It's way better at math, which admittedly might not be saying much. But it doesn't need a pencil, it doesn't need a calculator, and is never wrong. Never. This is the crossfeed. This handle pushes the tool in or out. I wind the handle in to take deeper and deeper cuts, making my parts smaller and smaller until they're scrap. That's how I know I'm done. Now the lathe has graduated dials, in this case in inches, to give me a better shot at making my parts the size I want. Now, lathes are made with one of two types of dial, direct read and indirect read. Direct read means whatever you dial in on the hand wheel is how much smaller the diameter of the work gets. To state the oblivious, lathes make round parts, and 9 times out of 10 you're interested in the finished diameter, not necessarily how much your tool moved. So on a direct read lathe, the hand wheel graduations and the diameter of the work are directly related. Move one whatever on the hand wheel, and your diameter would end up being one whatever smaller. This lathe happens to be indirect reading. I think all Colchesters are, but I can't be certain. The dials don't tell me what the diameter of the work is doing. They tell me how far the tool is moving. If I move the hand wheel, say 20 thou, you can see the tool post moves 20 thou. So in this case, we're reading the radius, and the diameter of the work gets 2 times smaller than what I dialed in. Neither is really better or worse, just different. Though it does stink when you're used to one type and you have to move to a different type. Taking a closer look at my graduations, we see that the smallest division is 1/1000th of an inch. So if I move the tool 1 thou in, I'm cutting 1 thou on the radius and the work gets 2 thou smaller. Say now I'm almost done with my part, really close to done. And all I have left to do is to remove 1 thou on the diameter and then, well, what do I do now on my dials? I'd have to do my best to split those divisions by eye. But how do I know that's half a thou? What if it's 4/10 or 6/10? Well, for one, you could use an indicator, set up just like this one, and not trust the dials at all. But that's still a really small move on a hand wheel. That and taking a 1 thou cut, or 0.025 millimeter, isn't as easy as it sounds. We're in the quantum realm here. Spooky stuff can happen, but that's a topic for another video. Instead, let's see if a little math can't save the day. This here is the top slide, or the compound. It goes by a lot of names, and by a lot, I mean 2. It's set 90 degrees to the cross slide, so that means no amount of turning this hand wheel will reduce the diameter of the part. Of course, if I turn my top slide to 90 degrees, then it works just like my cross slide, and I have the same problem. One division results in 2 thou diameter change, and I'm right back where I started. But check out what happens if I set my top slide to, say, 30 degrees. The scale reads 60, that's just how my lathe is laid out. But in this case, that 60 means 30 degrees off of 90, like 30 degrees off of parallel from the lathe axis. We've got ourselves a nice little triangle, with the motion of the top slide now 30 degrees to the axis of the lathe. If I wind the top slide in now, say a full turn, 100 thou, the cutting tool moves 86 thou in towards the chuck, and only 50 thou in towards the work, towards the lathe's center line. It moved the tool half of what I dialed on the hand wheel. If you didn't see it coming, that's because the sine of 30 degrees is 0.5. So now set up at 30 degrees, if I move the dial 1 division, the tool only moves towards the work half of a division. I can now, more confidently anyway, dial in a cut that would peel 1 thou off the diameter. No guessing between lines. If I were to set my top slide to 15 degrees, the sine of 15 is pretty darn close to 0.25. So that's 4 times less than what I turned the hand wheel. Now to get the same 1 thou off the diameter, I can move 2 full lines on the hand wheel, which is a ton easier to read than trying to split the divisions by eye. Dialing in 1 thou diameter reduction is a lot different than actually getting a 1 thou smaller part. apart. Frankly, being able to do that is what separates the wheat from the chaff, since, separating boys from men is no longer politically correct. Anyway, that's it. That's how your lathe does trig shop math all on its own, with no stinking calculator. Hey, so while we're here, you could also use a sine bar to set up your top slide. By eye, it looks pretty close to the 30 degrees we set on the scale, but here you could run an indicator along your sine bar and tweak your top slide angle until that indicator reads 0. I've also heard of people setting sine bars up against either like a test bar in the chuck or the quill of the tailstock, then mounting an indicator in the tool post, I guess, and sweeping this until the angle is correct. Again, until you had 0 indicator reading. I've never done this, and frankly, I don't know how you would hold this in space to even pull that off, but in theory, I guess it's possible. I would just load an indicator in the tool post and just watch the indicator reading as you move the top slide. So if this is set to 30 degrees and you wind it in 100 thou, if your indicator tells you 50 thou, half of whatever you wound in, then your angle is dead on. If it tells you 49 or 51 thou, well, you've got some tweaking to do. All right, I'm super excited about this. I saved the best part for last. Cosine error. Okay, fine, it's kind of dull. I was going to skip it, but I mentioned it earlier in this video, and I wasn't able to edit it out like I could time traveling using shop math, so let's give this some lip service. Now, I'm not a big fan of the term cosine error. It's not the cosine's fault, it's your fault. Come on, own up to it like a real wheat from the chaff. Cosine error is the error you can get from not aligning your measuring tool with the actual dimension you plan on measuring. Maybe it sounds obvious enough when stated like that, but usually it sneaks in more with test indicators than it does with dial indicators. But the concept is the same, and it's easier to demonstrate with a dial indicator, so we'll use this. It's actually a lot easier to demonstrate with a tape measure, but that'll just confuse everyone even more. Say we're trying to measure the height of this block. You'd be doing this on a surface plate, of course. Don't let anybody see you do this on a welding bench. If we're trying to measure the height of the block, it means we want to know this dimension. Of course, it doesn't have to be height. Maybe you're trying to measure runout, whatever, it's not important. But we have some dimension that we're interested in measuring, and in this case, we're using a dial indicator. Now, a dial indicator measures how far its stem moves, in line with the stem, right? If we put the indicator nice and straight, perpendicular to the top surface, we get a good measurement. But if we're not paying attention, didn't get enough sleep, or you got the whole shop heckling you for that karaoke bit you tried to pull off the night before, you might end up setting the indicator a little crooked. I mean, come on, it's not that much. What's the big deal? Say it's off 10 degrees for argument's sake. That'd be a lot, but let's say 10 degrees. To your bleary eyes, it looks good enough. Well, now you're no longer reading the height of the block. You're reading this line, this crooked line. Moral of the story, keep your indicator perpendicular to the dimension you're trying to measure. This is a 4-inch block of aluminum in the long dimension. If you measured it like a normal person, it says 4 inches. But if you insist on measuring it like a knucklehead, it's a 4¼ inch block. This is cosine error. The rule is reading 1 over the cosine of whatever that knucklehead angle is you're trying to measure the width of the block at. My apologies, I didn't mean to insult anyone's intelligence with those last 2 examples, but I wanted to convey just exactly what cosine error is. Earlier I said this comes up more with test indicators, because most people are pretty good at using dial indicators or a tape measure the way they were meant to be used. But there are all types out. Test indicator by nature turns an angle into a straight measurement. You move the arm a few degrees, but it tells you inches or millimeter. It's not giving you an angular measurement there. It's not reading out degrees. So here, cosine error can be a little bit trickier. It can sneak up on you. You have to know how this thing is meant to be used, how the manufacturer designed it to be used, well, so you know what direction it's measuring in. Now, every test indicator is different, so read the manual for yours. For interrapids like this one, they're designed to read properly when the stylus is about 12 degrees, I think, to the work. If you lay it flat, you're not going to get a real number on the dial. If for some reason you do have to lay it flat, or that close to the surface, maybe you're trying to get inside a tight spot, you'll have to add the cosine error for 12 degrees in the case of the interrapid. And of course, if for some reason you change the stylus on the end, if you use a longer one or a shorter one, well, you have to accommodate for that too. Usually they come with, or you can find little charts and tables to help you out. Now, this is pure speculation. I've never really cared much to look into it, but I'd guess that's 12 degrees, because 12 degrees is how much you need to clear the sort of that knuckle or the hinge in the back of the indicator. You can sweep an entire part, get accurate readings, and not run into anything, like you could if you held it flat. Also, that 12 degrees isn't super critical. If it's 10, if it's 14, if you're close, it's probably going to be good enough. That said though, test indicators like this are usually used to compare things, not to take a direct real measurement. Though of course you could if you took into account how it was designed. Maybe you're trying to use this to center work in a 4-jaw chuck, or center your mill over some existing bore or feature. You might not really care what the dimensions are there, just don't want the reading to change, or not very much anyway. Well, that's it, I think. That concludes our breathtaking, spine-tingling, awe-inspiring deep dive into the world of trig and shop math. Thanks for watching.
And now we'll go over a few topics in the book that we wanted to cover before we close this presentation. Reference planes and surface plates. Due to its physical properties such as surface hardness and low thermal expansion, granite is the material of choice for surface plates when tolerances are critical. All granite is not the same and, depending on the type, have different wear characteristics. The black granite or diabase is harder than other granites. The modulus of elasticity is 9.5 times 10 to the 6 compared to crystal pink, which is only 3.8 times 10 to the 6. However, due to the quartz content of 32% in the crystal pink, it will outlast black 5 to 1. The quartz content is the determining factor in the wearability of granite. Black granite is used primarily for its load-bearing capabilities. With any specific weight in black, it will be thinner than the crystal pink because it is literally a piece of rock with no particular mineral content. Whereas quartz content of crystal pink permits the instruments to slide much easier without any risk of wearing the plate. In general, crystal pink does not carry the load of black, but its thickness can be compensated to carry the same load. Remember, the surface plate is part of the gauge. It is the reference plane. As a part of the gauge, it must be calibrated, primarily for flatness. What is flatness? Well, it's more than smoothness as seen here. Just as you would clean any other gauge to accurately measure, the surface plate must be clean also. Do not use granite surface plates as workbenches or lunch tables. Dropping wrenches or hammers on plates can chip and nick the surface, and spilling coffee or drinks on granite can cause permanent stains. Grease from food particles will do the same. Be sure to set your workpiece to be measured down gently on the plate, as a sudden jolt or blow to the plate with a heavy metal object can chip or nick the surface. Also, when inspecting workpieces, especially small parts, try to use different areas of the plate because using the same spot over and over year after year will wear a hole in the plate. It's not really a hole, well, it will be a shallow spot. Basic rules for surface plate use. Set parts carefully on the surface plate. Dropping parts onto the granite surface can chip the surface. Rotate the parts of the surface plate used for inspection. Using the same area year after year can wear a hole in the plate. When using threaded inserts, use the minimum torque required to hold the part in place. Don't place heavier load on the table than the load rating indicates. If the load is higher than the rating, the plate can be permanently bent. Clean the surface plate daily using a cleaner recommended by the vendor. If not in use, cover the plate with a surface plate cover to protect it from dirt and dust. The bigger the surface plate, the more open the accuracy is. It's very difficult to maintain a very flat surface plate over a very large area. Angle measurement. It's interesting that there are essentially equivalent instruments in linear measurement and angular measurement. For example, steel rules in linear measurement have a similar type of scaled instrument for angular measurement, the plane protractor. The combination square is similar to the protractor head of a combination set. The vernier caliper of linear measurement is very similar to a vernier protractor when measuring angles. The micrometer, similar to index heads. Gauge blocks, very similar to angle blocks. Comparators, similar to sign devices with comparators. And measuring microscopes are similar to autocollimators. Squares are used particularly for 90 degrees. Other angles need other equipment. The sign bar is one of those devices used for determining very precise angles. The metrological features that are important on the sign bar is the reference surface on the top, the known center distance between the plugs or cylinders, And the functional features are occasionally attachment holes, a convenient center distance, such as 5 or 10 inches, and of course the plugs or cylinders. The sine is the opposite over the hypotenuse. So the hypotenuse is the distance between the plugs, and the important opposite side of a triangle is the gauge stack used to raise the sine bar. You can actually look up the angle in a sine bar table. Remember, there's a table for every type of sine bar based on the distance between the plugs. Here's a typical setup for a sine bar. Some sine bars are designed so they don't need 2 sets of blocks. They only need 1 set of block to raise one end. Sine bars are very precise. You can get them in different classes, such as a commercial class, which is accurate to 2.5 microns or 1/10 of an inch. Or you can get a laboratory class, which is good to 1.25 microns or 50 millionths. Sine bars are much more accurate at the lower angles. The higher angles cause it to be unstable, and you get less resolution on your angles per height that you raise the sine bar. This illustrates how much more stable the lower angle sine bar can be. If you were to take a rectangular solid and slice it at an angle, you will get a compound angle. Those are a little tougher to measure, and oftentimes you'll need a compound sine bar or sine plate in order to measure those angles. The compound sine angle plate is essentially 2 sine bars at 90 degrees to each other with hinges, as seen here. Here's a setup where you use gauge blocks for each set of plates at the opposite end from the hinge. There's also the index head zero spindle or dividing head, which is often good for angles and also rotational measurements such as runout. There are a variety of attachments that you can put on the spindles, including expandable collets, push arbors, chucks, and thread chucks. Another way of measuring or setting angles is using the angle gauge blocks. Note that on an angle gauge block, one end will say plus and the other end will say minus. Here it shows the 30-degree gauge block with the 5-degree gauge block set with the plus side at the largest end of the 30-degree gauge block. That makes a 35-degree block set. Now if you turn it around, it'll be minus 5 degrees, and that will give you a 25-degree gauge block set. Those are some of the key points we wanted to get across outside of those things that you'll learn from the videos. We'll see you next time.
Now, this ought to do the job when we get the teeth cut in it. The piece is not completed, but Roy has done a good job. And from here, other skilled craftsmen can carry on.